Here is one application of the Frobenius matching theorem that is perhaps not really expected. And this is a subject you can write books about, people have written books about, you could give a whole semester long course about. We will just do 10 minutes of it. So Latin squares. The name has historical origin because I think Euler, who came up with the idea, didn't put numbers into those squares, but rather Latin letters. We're going to use numbers. So what is a Latin square? A Latin square of order n, and of course n is a non-negative integer, it is defined to be an n by n matrix M that satisfies the following conditions. First, the entries of M are the numbers between 1 and M, each appearing exactly n times. Second, in each row of M, the entries are distinct. Third, in each column of M, the entries are distinct. And so here is an example. Here is a Latin square of order 5. In the top row, we put 1, 2, 3, 4, 5, and then we keep cycling. 2, 3, 4, 5, 1, 3, 4, 5, 1, 2. So each next row is the previous row, but cycled by one step forward. It's very easy to see that it's actually a Latin square. And similarly, you can similarly for each n, we can construct a corresponding Latin square. I can actually give it explicitly. The matrix Cij, actually Ci plus j, so the entry only depends on I plus j, where Ci plus j is I plus j minus 1 if I plus j is less or equal to, what is it, n plus 1, and otherwise I plus j minus n minus 1. So this is a Latin square of order 5. But of course, these are not the most interesting Latin squares. You don't have to cycle. Often you have a lot of other choices, some of which have further nice properties. In particular, a popular example of Latin squares of order 9 are Sudokus. They have an extra condition where if you subdivide it into 3 by 3 submatrices, those also have to have their entries distinct. So for example, this would not be a Sudoku, if not just because the order is wrong, because it's the 2 and the 2. So, okay. Now, so we have found a little boring family of Latin squares, but can we find others? So what would be a good algorithm to construct general Latin squares? So here is an attempt at a recursive algorithm. We just start by filling it the first row. All you have to ensure is that the first row has to have distinct entries between 1 and n. So the only option is that you just put in the entries 1 up to n in some order. Then the second row, now you have to be careful, you have to make them distinct, but you also have to make them distinct from the entries in the first row. And then the third row and so on. So for example, let us construct a Latin square of order 5 by this algorithm. So we've got lots of choices. Let me start with 3, 1, 4, 2, 5. Then I have to find the second row. Okay, this is a bit harder. I could do something like this here. And actually this is true. So far the entries have been distinct. Let's do the third row. It gets harder and harder with each step because you have to avoid a lot of entries. This still works. These are distinct, and all of them are distinct. Now you have to be even more careful. So we can do something like this. Well, except this doesn't work. This doesn't work either. You have to backtrack. Okay, so a 1 is a bad idea here. A 4 is also a bad idea, but maybe we can trade this 4 for a 5, and then you get something like this, except it doesn't work either. Maybe this will be a 4, except this should be a 1 then. Okay, does this work? These are distinct, these are distinct, these are distinct, these are distinct, and so on. Okay. And finally, the last row. And here you're in luck. You just choose whatever missing entries there is in the column. So there is no 4 in the column, so you put a 4 here, you put a 3 here, 5, 1, 2. And that's actually easy to see that here this entries will be distinct. Okay, so far so good. But does this work in general? In other words, will we always be able to produce a full Latin square by going row by row, so by using this algorithm? Or will we at some point have to backtrack, basically, or will we get stuck somewhere and have to backtrack? And interestingly, the answer is yes, or rather no, depending on which question you're answering. So it turns out that we won't have to, we won't get stuck. And what I mean by this, of course, we got stuck in building a row, but we don't get stuck after building a row. So if you know how to build a new row, you will never run out of possible rows to add. So this is the, so let me say it this way. We won't get stuck between two consecutive rows. Also, we might still get stuck while building a row if we just build it left to right without really thinking, without being strategic. And in other words, let me state this as a formal theorem, or actually proposition. So let n and n and k in 0, 1 to n, then any k by n Latin rectangle. And what is a Latin rectangle? Is basically an incomplete Latin square where you only have the first k rows. So it is any k by n matrix that contains that contains the entries 1 up to n, each appearing exactly k times, not n times, and satisfies the conditions 2 and 3 from the definition of a Latin square. So you still have distinct entries in each row and distinct entries in each column. So any k by n Latin rectangle can be extended to a k plus 1 by n Latin rectangle by adding an appropriately chosen extra row at the bottom. So basically, every time you want to add a new row, you can do this. And if you, of course, this means that doing it by just doing this recursively, you complete the entire rectangle, this entire square. And I'm sure you'll have noticed an error here. Of course, you cannot complete this Latin rectangle for k equals n. So k has to be at most n minus 1, not at most n. Once you have n rows, you're done. You don't have to, you shouldn't be trying to complete it further. Okay, so let's prove this. Let m be a k by n Latin rectangle. For example, so k equals 3 and n equals 5. It looks like this. We want to find a new, let's say, row that we can append to m at the bottom, so that the result will be a k plus 1 by n Latin rectangle. This new row should contain the numbers 1 up to n in some order, because they have to be distinct, because yes, the only way to do it is by just having them there in some order. Moreover, its ith entry has to be distinct from all entries of the ith column of m, and of course for each I. So how do we find such a new row? Well, we build a graph. Let G be the simple graph with vertex set. Okay, I'm just going to call it X union Y, where X is the first n positive integers, and Y is the first n negative integers, or maybe I should say the last n negative integers, depending on how you count. Okay, so what are the edges? We let a vertex I in X be adjacent with a vertex minus J in Y, if and only if J does not appear in the ith column of M. So for each vertex I in X, for each positive I, its negative neighbors are basically the numbers we can place in the ith position. They're the candidates. We have to choose one of them. And it is easy to see that this, so first of all, this is a bipartite graph. There should be no further adjacencies. So moreover, the graph G is regular, but it's not k-regular, it's n minus k-regular. Why? Well, for each vertex on the left, we have to count how many neighbors it has on the right. There is as many as there's numbers that don't appear in this column, but of course k numbers appear, so n minus k numbers don't appear. Conversely, for each number for each number j, how many columns are there in which j does not appear? Well, j appears k times, and it has to appear k times in different columns, because otherwise you would have two equal numbers in the same column. So there is, if it appears in k columns, it doesn't appear in n minus k columns. So this is not hard to see that it's actually regular. Thus, by the Frobenius matching theorem, G has a perfect matching. And as usual, so let's write this matching as 1 is matched with minus A1, 2 minus A2, and we're putting minuses here because the vertices on the right are negative numbers. So let this be this perfect matching. Then we can append the row A1, A2, dot, 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 AN to M at the bottom. Because each entry AI, it's matched with, so minus AI is matched with I, so which means that AI doesn't appear in the ith column. And as a result, obtain K plus 1 by N Latin rectangle. This completes the proof. So we have an algorithm for constructing arbitrary Latin squares, except of course we still don't really know how to build each row. But this is a lot easier, of course, than building the whole grid at the same time. And actually, so how do you build a row? You have to find the perfect matching. So this is where you don't need a criterion like Hall's marriage theorem, but an actual algorithm for finding a perfect matching. And as I said, this is something we will do next time. So brace yourself, we will have a complete solution to this problem very soon.